Alright, the September 2 bonus video, take 17 or something like that. Hello everybody, I wanted to try to clarify some confusion with the rules for rectangles that some of y'all were having. I also want you to understand, this isn't going to be a huge component of everything that we're learning within this class. I think this is appropriate because it helps us figure out where what we're doing comes from and maybe gets a greater understanding of what we're doing. But ultimately, it's not really a skill that I'm going to be constantly asking you to repeat and do over the course of this first half of the semester. Okay? So what I've got first off here is I've made a little doodle. Okay? I have an interval from A to B, and I've got a function f of x. And what I'm using the green marker for here, green marker, is that I know what f of x is. It's given in the problem or the setting. I know what B is, and I know what A is. Okay, those are all things that are known to me. And what the problem's asking for, the thing I don't know, is what is the area, or in general, the net signed area underneath this curve and above the x-axis. Okay, this is what I want to find. Okay, now there's a couple different things that one can do to try to approximate this. Right, first thing is, because I know A and because I know f of x, I also know what f of A is. Right, I know this point way up here. Okay, so what I could do is I could draw this rectangle right here and say, hey, the area of this rectangle is roughly the area of the function. We can see places where I'm definitely wrong. I'm not counting this at all, and there's a little sliver up here. Well, I am counting this, rather, and I'm not counting this little sliver up here. But it's a place to start. Okay? Now, what is the area of this rectangle? It's the width times the height. The width is b minus a, and the height is f of a. And I'm going to mark this as the area using the left point. All right? And that's easily where we can start here. Is this still like adjusting my zoom? No, it's adjusting my lighting. Okay. Another piece of information that I happen to know is, because I know b and I know f of x, I know what f of b is. Because of that, there's a whole other rectangle that I can draw that looks something like this. Okay? Again, wrong. I'm not counting all this area, and I'm counting a little sliver right there. Okay? But what's the area of this rectangle? Well, it's the width times the height, in this case, is f of b. And I'm going to call this a sub r, the area using the right point. Okay? Now, how can we make this approximation better? If I look, the function varies a lot over the interval from a to b. So what if my cat stops playing with the cardboard box in the room? What if I make smaller rectangles, right? If I make rectangles happen more often, they'll better capture that change as the function goes along. So I'm going to put a little point right here, and this is going to be the midpoint. So this is a plus b over 2. Okay? And I can extend a rectangle from there, and I can either use the left endpoints, which looks a little something like that. And those rectangles would be, if I write it down in all of its uggo glory, the width of this is a plus b over 2 minus a. So that's b minus a over 2 times the height. What rule did I use? I made a really bad picture. I apologize. There. Adjust your thinking promptly. Okay, the height of that is f of a. Or I can use this rectangle right here, with the width is again b minus a over 2, but the height this time is f of a plus b over 2. And that could be a new approximation, again, using the left endpoints. Okay? If I wanted to use the right endpoints, then I'd have the width of the first interval times the coordinate of the right endpoint plus the width of the second interval times the coordinate of the right endpoint, and that would be a new approximation using the right endpoints. So we can see how we can go from one rectangle to two rectangles in either approximation and potentially get better. Okay? Now, if you carry this rule out to its fullest, okay, what you would have is we make a sketch of our function again, a, b. Here's my function, f of x. Okay, we do what I defined as partition. And so you make n intervals. And I'm going to put slash cuts. So I'm going to go bo 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 bo. Okay, that's my n or whatever. Okay, and so I don't run out of letters. Let's call the first point x0. The last endpoint will always be xn. And then the next one is x1, x2, x3, and so on and so forth. Now, the way we cut this is that we want x1 minus x0 to be the same as x2 minus x1, to be the same as x3 minus x2, to be the same as ... to be the same as xn minus 1. And we are going to define this quantity as delta x, and the way to find it is just to take b minus a and divide it by n. So that will, regardless of how we choose our height, that is always going to be the width of any rectangles we draw. Make sense? Now, if we use a left endpoint approximation, okay, what are we going to do? My first left point is x0, so that's my height times the width. My next interval is going to be x1 times the width plus ... all the way until I get to the second to last point there. And we can write that a bit more conveniently by doing the following. I recognize a pattern here, 0, 1, 2, 3, 4, all the way up to n minus 1. So I'm going to take I as the index, and it runs from 0 to n minus 1, f of x sub I delta x. And that will be my left endpoint rule. The right endpoint rule, the only thing that changes is that my index is going to start at 1 and end at n. Because, and prove that to yourself, that's how you get all the rectangles using the right endpoint. And so these are my two rules here that are fairly standard. Okay? What the actual area under the curve is, according to Riemann, is I can take the limit as n goes to infinity of I equals 1 to n, f of x sub I star delta x. Now, what this means here is any rectangle height. And so if I were to take, let's say this is xi, and this is xi plus 1. So any interval, and here was my curve f along there, I could use my left endpoint, I could use my right endpoint, I could use whatever's in between the two of them, I could use something over here, I could use something over there. Ultimately, it doesn't matter, because as I let n go to infinity, this delta x here is b minus a over n. That goes to 0. And so this width goes to 0, so any point I pick in between is just going to kind of squish together and end up being the same point. Does that make sense to you? Okay, and so that's basically the relationship. That's the definition of xi star. Those are the definitions of the xi's, and hopefully that ties it to like whatever the exact area is. Now on our worksheet, I asked for you to like, well, what's the midpoint rule? And so if I have xi and xi plus 1, and we have formulas for these. this is the same as x0 plus I times delta x. And this is the same as x0 plus I plus 1 delta x. Okay? If I want to necessarily use the midpoint between those 2 points, well, I can calculate it. It's going to be the left one plus the right one divided by 2. Right? And so if I look at that, I'm going to get an x0 over 2. No, don't lie. Don't be a dummy. Okay. x0 plus x0 is 2x0. And then I delta x plus this is going to equal 2I delta x plus delta x. Make sure that makes sense to you. And then I divide that whole thing by 2. So then if we look, what is the formula of the midpoint? It's x naught plus I delta x plus, now go ahead and take a half step, right? Where do I start? How many times do I jump by delta x? And then jump by half as much again. So this right here is the definition of my midpoint. Now, if I know the function across there, I also know the height of that rectangle, which is f of mi. And so my rectangle for approximating the area becomes something like this. So it's not using the left endpoint, and it's not using the right endpoint. It's using what's in the middle to determine the height of the rectangle. Kind of makes sense? What about trapezoid? The trapezoid rule says xi plus 1. Rather than making a rectangle out of this, let's go ahead and connect these 2 points with a straight line. All right, so now I've formed a trapezoid where the area of that is just whatever the area of this rectangle is plus the area of this triangle. Figure out the formulas. All right, that's part of the goal of that exercise. Okay. The last one, which was kind of experimental on my part, which says I've got a left endpoint, I've got a right endpoint, and I've got the function, is to say rather than using any value of the function here, I want to know what is the average slope. So somewhere in here is a point C, where at that point in the function, the tangent line is the average slope. Form the trapezoid using that. What you will see is this height right here of this rectangle doesn't depend on what f of x is. It depends on the formula for this line. Let's go ahead and call this t of x, which is the tangent line of f of x at point C. And the height of this one is also going to be defined by that curve. We know it touches right here at f of c. And we know that the slope of t of x is equal to the slope, or rather, excuse me, the average slope of f of x on the interval xi to xi plus 1. This one is, by design, going to be tough. Okay? And something that you will learn about a lot of these exercises, a lot of the learning is in the doing and trying, and not necessarily completing it all and getting all the perfect answers or the whatnot. Okay? I hope this helps. Stay healthy.